So first, I will try to motivate you. Why should we care about it? Because of course there are the laws which impose you why you should care about it. That's the 10 million euro. But some practical point of view why you should care about cybersecurity. Then I will show some analytic hardware. I would say I'm a little white hacker, and I'm also amateur radio, ham radio. So motivation. Why should we care? IoT. So this is an outline of this section. I would say that IoT is the new term for embedded. I'll show you why. What security challenges this brings. Then we will go through an example from smart metering world, and I will explain what I mean by effort required versus assets protected. This is very important when you think of security. When the asset you protect is not so important, you don't need to, you will see it in the presentation. And at the end, a very interesting idea that sometimes a very small change can have a very huge impact on the security. So the security, of course, there will be a lot of standards, which it's good to go through them and implement them, but sometimes it's also good to think of it that things are not like 60 pages of document you need to remember by heart, but it's sometimes really about small changes. So, why I say that IoT is the new term for embedded, because if you check this graph, you will see that from 2010 to 2020, the number of connected devices was multiplied by 5. And the world population rised only by something like 600 million people. And maybe an interesting line in this graph would be how many software engineers and how many security experts, what was the rise of the number of those people, because more devices you have, more people you need to have in the security. So maybe it will be flat as well. So because of that, the security risk is rising. More devices you have connected, higher is the security risk, of course. Also, the cost of the connection overall is smaller and smaller. And now I'm talking about modules, about radio chipsets, about some monthly fees for the connection. Talking about narrowband IoT, for example, you can have 10 years connection for $5. It's basically for lifetime of your product, you can have a $5 connection. This would be something unthinkable in 2010, that such price for internet connection for your device. So the cost is reduced, cost of the device is reduced, and of course, naturally, cost is the first parameter for every product. When you are going in this direction by reducing cost, you of course might also reduce the cost of the hardware itself, so you might put away some of the security. So that's also maybe why, because of this trend, to go against the trend, there is EU who tries to impose some security. So back in 2000, it was normal to have some kind of administrator for any internet-connected computer or PC. Go and tell to your customers that for your IoT or smart microwave oven that they should have somebody who takes care about the device to have an administrator, because this device is internet connected. It can do anything on the internet if attacked or if controlled by a hacker. So this is very interesting to think of it, because IoT devices, they are sold like if it is a hair dryer, for example, or a lighter, so it's dirty cheap, but they have, from security perspective, they have sometimes the same capability as a PC connected to internet. So this is interesting to think of. And another aspect, this will address the GDPR. The small devices, the IoT devices, and your PC, they both contain end-user personal data. Today we will look at smart meters and how they contain your personal data. So this is another point. And of course, the end user is not aware of security risk. They look at the features, they want the things to be smart, they want to benefit from these features, but they don't understand the security, they don't care about it, so that's why they just leave the default password. They want the thing to work, they don't care about security. So the human factor, which I mentioned, plus only just emerging standardization in device security is what brings the Internet of so-called insecure things, as I call it. It's not nowadays. It's not Internet of Things, but I would rather say Internet of insecure things in a lot of cases. So, example of where it is an Internet of insecure things is smart metering. Very often, unfortunately, there are some good exceptions, but we will get to that. So, if you can think of an average flat, maybe also here in Prague, but in any city, if you have 2-room flat, you need 2 water meters, you need some heat cost allocators. Those are small plastic boxes on radiators. So you will have 2 water meters, maybe 5 heat cost allocators for 1 flat. So it is something about 7 smart devices which are not directly but indirectly connected to internet. Of course, if you multiply this number by the number of flats in Prague or number of flats in Czech Republic, you will get a very huge number. And of course, because of that, the price of these products is pushed low a lot. And therefore, this thing is very susceptible to what I mentioned before, that it is very likely that the security will not be the first thing people designing these devices will think of. One good example is that some manufacturers, they implement the standard wireless M-Bus protocol, and I will show how wireless M-Bus is taking care of security or trying to take care of security in some generations. Or they implement their own proprietary radio protocols because they think that it will be maybe a vendor lock, so from business point of view, that's the reason maybe. Or maybe they think they will make the security better, but when you think that you will do the security better than some standardization body, this is always a bad idea, don't do it. There are some good companies from security perspective, for example, Kaustru. They take security very seriously, but some of them they don't. Yeah, I will not, of course, name because this would be good for them, and I don't want to. I don't want to do any bad for anybody, but I will say what I encountered in the market. So a custom cipher based on sorting and some nibble replacement. So basically. Security by obscurity, this is very bad. And another thing, sharing the same key everywhere. Or, if not sharing it everywhere, the reseller of this product, of the water meter or cost allocator, from practical reasons, is using the same key everywhere. Because as a manufacturer, well, he orders a batch of 100,000 devices, and the manufacturer will ask, what security key you want there? Well, to keep it easy, let's put there all zeros. We have IS 128, we have all zeros keys, but it's okay. The tender, where we want to go, they ask for IS, we have IS. Nobody asks for the key, or what should be, or how strong should be the key. Yeah, and this is real. There are devices with all zeros key in Czech Republic. I will not tell where, and I will not. But there are many thousands, maybe tens of thousands. So another point is using key derivation based on device identification. This is like you try to be smart. So okay, it's bad to use the same key everywhere. It's bad to do XORing or nibble shuffling or any. Also, Caesar cipher is used. So you rotate the byte value, and you try to hide what you send like that. So instead. You say, okay, I will use encryption key derivation based on device ID, because nobody will think of the smart algorithm I use, which will take the 4-byte device ID and will generate some maybe 1632-byte key or something which I XOR with the payload I transmit, and this creates the security. The bad thing is when you don't protect this algorithm, then this leaks, of course, and any security based on keeping algorithm which derivates the key secure is not good. The security should be based on keeping the key secure and private. Okay, here is an example of how this is standardized in wireless and bus. There is something called open metering standard, which is not directly part of wireless and bus standard, but this rather extends and helps manufacturers who want to be standard and interoperated to implement something which can be easily read out, talking about water meters and resource allocators. From security perspective, there are 4 approaches. The first one is used very often, and somebody is smiling and they say how they can handle the security by having no security at all. Well, sometimes it is better to know that your data are not secure at all. It's better than just thinking that they are secure, because if they are not secure at all, you just deal with that and you know what's the real state of things. But if you use some kind of security and you don't do properly key distribution and key management, then maybe it is better not to have security at all. So next security profile is using IS-CBC. That's the security profile A, security profile B as well. There are some differences, like the security profile A is using a static symmetric key, whereas the security profile B is using a derivation of the key. This is not to be. This is not the same as derivation of the key itself, because the key is derived and it is ephemeral. So it is used for a certain period, but it is derived from a different secret, from a real secret, not from an ID which is not secret. And then there is the last one, security profile C, which is using TLS to do the encryption. There was a conference in 2013 in USA called Black Hat USA 2013, and Swiss company called Compass Security did an interesting analysis of wireless and bus and of the standard. And they found out, and they show it in the presentation and also in the document, that as you can see here, it looks like standardized. It's using IS, CBC, everything's good. It looks secure, security profile A and B. If you are a manufacturer, you look at the profile C and you think, oh, that's maybe too much, let's keep it simple IS and it will do. And you implement it exactly as in the standard. But the problem is, it's still not secure. They have shown that you can, the effective size of the key is only 64-bit because of the initialization vector, or how the initialization vector is constructed in IS 128 CBC in case of wireless and bus. They have shown that even if you do encryption, the zero consumption detection is possible because of that. And very often, of course, when you sell a water meter, the value which is there is 0. So if you are an attacker and you attack maybe, or you want to know what's the key, or you want to know, you want to attack some water meter, the value you can expect the most is 0, because when there is no consumption, the value which is transmitted is 0. So this is also very bad. And that's why the security profile A and B should not be used at all. I can tell you that I have not met any device in the market yet in Czech Republic which is using security profile C. So just interesting, but it doesn't mean it's not secure. It just means that the security is lower then present it. But it is secure, but it's not 128 bits. And I will get back to the upper part of this slide. That's why IS-128 CTR, the counter mode, is more suitable than CBC, and it is also possible to use CTR and still be part of or be according to wireless and bus and according to OMS, because this counter mode is less sensitive to badly chosen initialization vector, and it is more robust against chosen plaintext attacks, because this is somehow related with the zero consumption, of course. When you know what's the plaintext, what was the payload before transmission, before encryption. So the countermeasure would be to, of course, use security profile C, or to use custom. I don't like to say, but to use a custom way how you construct the initialization vector so that you don't deteriorate the security. This slide is trying to explain what I mean by effort required versus ASIC protected. If you think of the value of the water meter is not so secure as the PIN code of your credit card, for example, because when you look at the water meter, you see the value which is there. So one single water meter is not like critically critical, or it's not security critical device, because you can just walk in, look at the water meter, and you have the value. That's not the issue. The issue is when there is some common weakness in the water meter, which can be used to wirelessly read values from the whole fleet of the water meters. That's a problem, because then, of course, if somebody who has bad intentions stands in front of a flat house and simply looks at the value of which is on the water meters for 1 day or 2 days, and when there is no change in the consumption, then it means that there is nobody home. So it's just as easy to really see what's happening. So it's basically you have sensor of presence of people in the house. You can, like this, you can also detect how many people is there in the flat. You can detect when they are taking shower, because some of the water meters they send the data every 15 seconds. Some of them they send it every minute, every 3 minutes. So if you think of it like this, water meter is a device which contains private data. Yeah, it's not directly, but indirectly it contains private data, because if the key is leaked, anybody can know when you're taking a shower, for example. So the key is to mitigate common weak points in the design of your device. I try to very quickly explain how or what can be the simple countermeasure. Of course, custom cipher, don't use custom cipher. You always use AS instead, anytime. It's not taking so much flash. AS 128 or 256 in counter mode takes approximately 950 bytes of flash if you are using I implemented that on STM32, for example. So a 32-bit ARM architecture, 950 bytes. I know it is always good to optimize the flash size to buy the cheapest microcontroller with the smallest flash possible, but 1 kilobyte of flash is not that much. And of course, if you implement the custom cipher, it will also take you some space in the flash. So it will maybe not be 950 bytes, it will be 200 bytes, it will be a single small function with some byte shuffling, but it will take you some. So please go and always use AS when you want to do ciphering. Sharing the same key everywhere, well, that's quite evident. Just don't do that. Use per device unique key. So in the production line, always do provisioning and burn. It can be either use a secure element, that's ideal case, or if you can't, you can burn the key in the one-time programmable memory, for example, in case of STM32, in case of different well, in NXP also has one-time programmable part of the device, and different manufacturers, they do the same. And the reason why there is this one-time programmable part in the flash is because this is used for flashing some parameters. If you have some analog circuit to flash, there's some offset, some calibration data, and of course it can be used to flash the key and to keep the firmware in the real flash and the key in this separate part. Key derivation from ID, well, of course, don't do that. Instead of that, use some true random number generator in production to generate the key, and then use this key on per device unique basis. So if you look at that, it's like one kilobyte of flash size. Of course, this means some change of process in production. This is not trivial. It will cost you some time and money to implement that in production. You need to have some database where you have ID versus key matching. And when you sell some range of device ID to your customer, you need to have some way how to communicate that for this range of IDs there are these keys and your customer need to use it. Of course, it will be complex, but it doesn't need to be complicated. It can be an Excel file which will be zipped with the password. Yeah, that can be the way you distribute it. It's always better than having the same key everywhere. So, as I said, small change, big impact. So now we are getting to the part where I will show the analytic approaches which can be used to analyze devices. So I will let you see the hardware yourself. You can just look at it and then let it continue. This is the device I analyzed. Maybe this form is not that interesting. I have brought the device in a form where I soldered some points, which I then used for analysis. So first we will look at the hardware and hardware tools. So we will check what are general analytic steps. So if you give me a smart meter and you tell me, okay, Marek, look at it and try to hack it. Go and hack it. You will not tell me anything about it. So how I will do it. Next, I will show how easily you can do power analysis. The device you are trying to breach or you are trying to develop as well. It's the same very often. How you can do mixed signal analysis using Sala logic. Who knows Sala logic from this room? Okay, a lot of people. And at the end, I am showing spectrum analysis. So if you don't touch the device at all, you don't open the case, you can still hack the device because you have software-defined radios. Okay. So what are the general steps or the general recipe to hack a device? It's not complicated. So if you give me the device, I will first gather all available documentation on the device. This is really important because in the documentation, an interesting thing which happened, I was trying to analyze a frame which is transmitted by a device. And if you think of, you are a documentarist, you are somebody who is writing documentation. In the radio frame, there are some data. In what order you will write the data in the documentation? If you look at the frame from left to right, there is device ID, then there is, I don't know, how much cubic meters was transferred, then there are some error flags, and then there is some CRC. Let's keep it simple. In what order you will write the bullets in the documentation? Well, you check the frame, and then you write simply it as it is. In the frame, you write it in the documentation. So this is very helpful. You don't even need to touch the device to guess in what order the data are in the frame. When you are trying to analyze some device, what you need to do, you need to try to think as if you were the developer. what I always try to imagine, okay, I'm a developer, I have a manager who is pushing me to finish it because of course the deadline is behind me, and I need to have it done, and I need to have it done very quickly. So what would I do? How would I do it? Would I think of how I should mix the bullets in the documentation so that I don't give any hints to potential attacker? No, I would simply write it as I see it, of course. So this is an interesting point. Look at the documentation always. So that's funny, but if there is a bad documentation, you have high level of security. Just a funny point. Second, you perform power analysis because that's very easy to do. You will see. Using, you can use Oticoitec Arc. I do a little promo here to do that product, but you can use also, I think Nordic Semi did some tool to do power analysis as well. It's even more affordable than Oticoitec, but I strongly recommend you to use this Oticoitec because it's much better, and you will see. And a very good feature is that it can synchronize the power analysis or the power profile you see with UR output, with GPIO, and with any other ADC you sample on the board. So you can really see when some logical signal is flipped, and then you can see that power profile does something. You can guess what's happening in the device. Like here starts the narrowband IoT transmission. Here starts the wireless and bus transmission. Here starts the receive window after some offset, etc. Yeah, so those things can be really, you can read. I sometimes, even when when there is documentation for a device which I am trying to integrate, sometimes even if I have the documentation and I have the information after how much time the device should open the receive window, I prefer not to look at the documentation and the numbers in the documentation because, of course, those are just numbers on the paper. But I prefer to connect this Oticoitec and to really see what's the power profile, because you can have a sub-millisecond timing and see what's happening. So what you do with the power profile, you identify repetitive patterns, of course. You identify transmissions. Those are rather higher peaks in consumption. You check the reception. Those are like average peaks in the consumption. You check the sleep current, and you check some transitions in between, which can be some calculation which happens in the device, etc., some processing. And you can use that for timing. You know how often the device is receiving, how often it is transmitting, what it is doing, etc. You can do the analysis short term. It can mean like 10 minutes record. You can also do the analysis for 1 week, 2 weeks. It's possible to record it so long, and it is quite. And because you can do this matching with digital signals, if you know what to look at, you can simply let the device run for a whole month, and when there is the readout period at the end of the month, because some meters are not read out every day but only once per month, and something happens, you have to record it and you can check it. Third part, of course, if this is not enough, you didn't have to open the case until step 2, and there is step 3. Okay, so you use your soldering iron or with this knife end, and you open the device, so you don't trigger any mechanical intrusion detectors, which are there sometimes. So you can use hot knife to open the plastic. You connect to all serial buses, SPI, I2C, UR, GPIO. Of course, how do you guess where are those buses? Well, you check what's the microcontroller, you check documentation of the microcontroller, and you simply connect solid logic. You have 16 signals. So you can connect even where you don't think it will be interesting, but you better connect more than less, and you start recording. From that, you will see what you can see, but you can really see a lot from that. And the interesting part of this is that you can sample not only logical level, like digital value, but you can also see analog value. So if you are not sure of what is the signaling used, or you can like that you can detect high impedance state, input state, output high, output low. So not just digital signals, but also like in what state the pin is. Can give you also some hints. And the fourth is, of course, print the paper data sheet of all chips which are inside of the product, especially the register map of the radio is important. Then take the SPI communication, find a very good, comfortable chair, and start analyzing the hexadecimal stream, what it means. This is very hard part because, well, I used to do that at night, because at night nobody will call you, nobody will mail you, nobody will text you. So you are in a serenity, and you can check the hexadecimal stream versus the register map, and you can slowly, little by little, see what's the carrier frequency, what's the deviation, if it's FSK modulation, for example, and you slowly decode the settings of the radio to see where the communication is being done. Now I have 2 children, so it's a little bit harder to do it. So you need to really turn off your phone, get closed in a room where nobody can enter, and you can spend like 8 hours, 2 days analyzing the hexadecimal stream. Okay, so now I will address the steps. So for power analysis, this is the Otykoitek, which is being sent to you. You can check it physically how it looks like. There are 2 models. There is ARC and ACE. One is going up to 25 volts, and it is galvanically isolated. The cheaper one is ARC, and the more expensive is ACE. ACE is galvanically isolated, and ARC is not. It goes only up to 5 volts. But for IoT devices, this is good. If you want to have some device which is maybe 12 volts powered, well, it's maybe good to have the more expensive one. This is how the graph looks like. So you have current consumption. You can see the peaks. You can select some part of it. I didn't show the synchronization with UART, but basically here the window is split in 2, and you have the UART output. And when you click on the line, it will show you in the power profile where it is. And when you select some lines in the UART output, you can see some area being selected in the graph, and it will give you on the upper right edge what's the energy consumption. And it's in milliwatt hour, which is not that practical. I prefer to see it in milliamp hour, but if you simply divide it by the voltage you have milliamp hour. So here, for example, you can see what's the cost of one transmission. I think it's maybe narrowband IoT or something like that. I said that you can use it for detection of how periodically the device is sending data. What I'm showing here is so-called TAU. It's a tracking area update for narrowband IoT. In Czech Republic, it is 70 minutes. So you can see every 70 minutes the narrowband IoT device there's an impulse in the power consumption, and you can detect it. Like, it is very simple example, but you can have the idea. Of course, if you go into the microamps, it has quite good resolution in maybe even 2-3 microamps. You can see the change. So quite good dynamic range of the measurement. It tends to be noisy sometimes, but if you take care of it to be as low noise as possible, you can see things happening. We go to the next tool. This is Sale Logic Pro. This is the most expensive model from Sale, but I really recommend you, if you do electronic design, you need to have this on the table of your developer, because oscilloscopes are great tools. I have background from Department of Radio Electronics, so I like oscilloscopes, I like spectrum analyzers, and I like proper tools. This is not a proper tool because it's PC connected front end, So from really like a signal capture or exact measurement, this is not a great tool. It is not like calibrated, etc. But when your task is not to do super exact measurement, but your task is to do analysis, you don't need to have super exact measurement. What you need to have is something which is user-friendly. And oscilloscopes are not user-friendly when you try to export the data to PC and then do some analysis. It's very tedious. It's not. It's a lot of work, and you will very fast. Your manager will come and say, "Hey, stop doing that. You're spending too much time. You need to do that. Just forget the analysis. It doesn't matter. We will not have it." But if you have this tool, it's you connect it to up to 16 places on the PCB, and you can look at a lot of signals, and you can correlate. You can think of what is the relation between the signals, etc. Show me 16-channel oscilloscope which can go up to. Oh, I didn't put here the numbers, but it has 12 bit and it goes up to, I think, 15 megasamples in analog, or maybe just 20. It's not like 1 gigasample, but even 20 megasample in analog sampling plus minus 10 volt, it's quite good for basic analysis. In digital, it can go, I think, up to 100 megasample, which is not, again, it's not 1 gigasample, it's an oscilloscope, average cheap oscilloscope, but for a lot of SPI signals and I2C, it's completely enough.
It has many protocol analyzers,
yeah.
many different protocols.
I will show one later, and of course this is also interesting. When you only have the digital signal, you look at it and oh, it looks like I2C, it looks like SPI, but go and analyze bit by bit manually. That you would need a really good chair to really comfortable where to sit. So no, don't do that. Instead, you just need to guess in what mode, for example, the SPI is running, what phase, if clock is idling high or if clock is idling low, etc. You do the settings and you have the raw signal, and then you have the analyzed hexadecimal values, which you can export in Excel, and then you can analyze line by line what is the meaning of every byte which is sent over. Okay, so I think I went through this slide, so we'll move forward. This is how it looks like, how the user interface looks like. So you can have like this analog signal, of course, this sine wave. You have digital signals. You can very easily see the timing, and because you are sampling at 100 megasamples, your time resolution is quite good. So interesting thing is I was analyzing one device, and it was like two devices from the same manufacturer. And I was able to receive one, but I was not able to receive the other. Even the tool which was used by the manufacturer to receive those two devices was the same. And I was thinking, like, what's the difference? What changed? Because it should be the same protocol. I look at it, and then I realized when I was analyzing the length of logical 1 and length of logical 0, that the newer device had a bad clock. It used some internal RC oscillator, and during the transmission, because the power was dropping a little bit, the frequency of the oscillator was changing a little bit, and during the transmission, the bit rate was changing a little bit. So I had to do oversampling, and then from the oversampled signal, I was able to recover the data. Yeah, so basically, like that, I discovered that there was some bug, hardware bug, which they of course were aware of, so they did the oversampling on their side, but I didn't do that because, well, it worked for the generation, and I think it was like the newer was worse, or maybe it was the inverse, I don't know, but that was interesting. So sometimes it's really important to look at the details, not just logic 1, logic 0, but here it is evident that the length is not the same, but even if it is just shifted a little bit and it is glitching towards, I think they were running at something like 9,600 baud, and it was faulting like that, so I had to do software over something. If you want to go even further, because here you can see that this is a simple UART, async serial, and you can see the ASCII value K, I, etc., which is good. But when you have some SPI communication and you guess what's the phase, so here you can see that the clock is idling low, and you have 8 bits per one transaction. So here you see MISO and MOSI, master in, slave out, master out, slave in. And you can, of course, take the data sheet and look at the bytes, and on a piece of paper write what's happening. Like now he's setting the frequency, now he's starting the transmission, now he's filling in the FIFO, now he triggers now the transmission starts. I can see it also in the power consumption that now it started. Yeah, and like this you do the analysis. Or when you are lazy, and it is good to be lazy when you are a developer, you can check whether there is not a software analyzer plugin, or you can write it. It's some work, but I call this a scripting illness. I have a friend, and if he needs to do 10 minutes work manually, he prefers to spend 2 hours writing a script which does the 10-minute work automatically. Yeah? So this is something similar, but it is not about the time. I always am explaining, yeah, because time, cost, etc. So I try to explain it's not about the time, but you can make an error. When you do the analysis manually and you do an error, you can run into you can get lost, yeah, during the analysis. So that's why it is good to write a script which you use the data sheets to write an analyzer, which will then show you what you can see on the first line, which tells you, for example, that he's writing to a register modem config 1, and he's setting bandwidth to 125 kilohertz, coding rate at 4 divided by 5, and that it should use explicit header. Yeah, this is for LoRaWAN, for example. So you don't even need to look at the hexadecimal values, but you directly look there and you see what's happening. So really, it's like in Czech we say on a silver plate. So and of course, when it is not possible to open the case, or when the case is so badly hidden, or when it is simply not possible to get directly to the signals, you still can do the analysis. But of course, it is good for prevention to route the signals to the radio in that way that a potential hacker will have a very bad day. So I advise you to do so. But if you want to really prevent or increase the effort required to hack the asset you protect, so it's good to do it, but it's not, of course, like the final protection. And even if you do it, the attacker can have one of these, either Adam Pluto, hack RF1, or RTL SDR, which is very cheap, which you can see physically, and can capture from kilohertz up to 2.4 gigahertz or even more the signals. What you can do, you can remove the antenna, so you really capture only the signals which are close. You can close the device and the SDR in some improvised chamber. It can be like a big pot for goulash, for example. You put it inside and without the goulash, and you capture the signals which go out of it. And again, you can record for many hours, and if the device transmits from time to time, you capture it, and what you will do first, you will look at this. This is called water flow diagram, and just to explain, who is familiar with that? Okay, so but I would say majority is not, so I will explain. So you see the signals here, for example. You can see that it looks like those are two different signals, and that they are not FSK, but they are rather ASK, because there is some pause in the transmission, and it's a single line, so it's a single carrier. If you see two signals side by side, maybe this one is playing white, so if we would zoom in, you would see that there are two two lines like this, you can see it's like frequency shift key, FSK. And out of that, you can receive the signal, and you can demodulate it. You can have what you would have if you look at what was written in the radio chip. But it's a little bit more work because you need to guess what's the synchronization word, etc. But it can be done, or you can simply use what you capture, oversample it a lot, and then you simply guess the coding word. I also performed one analysis like that because I didn't have physical access to the device. So what you can do, or what I did, you can write. It's very simple but you need to have some decent knowledge of modulations and DSP. But again, DSP is not like magic. It's mathematics. So if you know mathematically how modulation works, you can write an SDR receiver, or SDR-based receiver in Python. So here I simply instantiate the Pluto, which is the name of the SDR. I tell him what will be the bandwidth where he receives, and then what I do in the rest of the script, which I don't show here because we don't have time for that. I try to I do short-term spectrum analysis. So I receive the signal and I segment the signal in parts, and I try to detect two frequencies or two frequency bands where the power is highest. Like that, I detect like where could be the FSK signal and what will be the deviation, the distance between logical 1 and logical 0 signal. I use these settings, and then I try to demodulate the signal and to show and to plot 1010 diagram, like time diagram. And from that, and of course, very often when you have a smart metering device, it is transmitting the same frame again and again, or the same length of the frame again and again. So you can then use length of this signal as a filter, like software filter here in the script. You filter out frames which are not interesting, and like this you basically can build a universal FSK receiver which receives in a certain range of frequencies, which don't care about what's the deviation, and you can then, I just let it run. It generated a lot of gigabytes of records, segmented records, and then out of the segmented records, I try to find those which are interesting. I try to correlate them, and like that you can guess this part is changing. This will be device ID. This part is not changing. This is the synchronization word. And you have the beginning. And when you have the beginning, well, you don't stop until you have it all. So that's how you can also proceed. So if you want to really deep dive, or you have some decent knowledge of radio and DSP, SDR is also the way to go for analysis. So that's it for hardware tools. I was a little bit talkative, so maybe I will move a little bit faster so that we have time for the practical part, but the practical part is not that long. It basically shows what I already explained. But now we are getting to the software tools. I will very quickly show you Binary Ninja and Ghidra. Is somebody aware of those tools or no? Okay, 1, 2, 3, 4, great. So both are tools which you can use for analysis of binaries, DLLs, or any software. You can decompile the software and you can look inside. And it is completely legal to do it, and it is open source, and you can go and do it. The mantra of the tools is everything is open source if you are able to look inside. Every binary is open source if you are able to look inside. So don't compile in your binary the security keys. They are open, they are available to everybody. That's why from certain, like if you remember, like in 1990s, if you had some computer game, there were these modified exe files which you just put in place and you didn't have to pay for the game. Yeah? Of course, the number and the tools available, there were not so many of them. So there was quite a few people who were able to do this analysis. Nowadays, with those tools, it's really simple to do. And that's why all games today, they need to have internet connection, they need to ask for a key. They maybe let you play offline. I don't have time for playing, but I know the theory. they let you play offline for 1 day, but then the key expires and you can't continue, etc. Yeah, so when the security cannot be built in the binary, it must be built on some on the fact that the program talks with some remote server. So that's the first part. And second part is dynamic runtime analysis. I call it like this, but basically I will show you what happens when you forget to disable debug port on your microcontroller. And I will show it on an example of MSP 430, so nobody from TI is here, I think. So you're fine. But it's of course anything. Any microcontroller can be attacked like this if the manufacturer doesn't disable or even physically destroy. It's possible to really break the connection of the debug port to the. Or another way how to do it is to have debug authentication. That's also something which is very good, and in Acryos we cooperated with NXP on development of debug authentication in Russian. Okay, so static code analysis. So let's imagine you have the binary, the firmware, or you can have firmware update file, or you can have some configuration software which is delivered with the product. And what you will do if you want to see what files can be interesting, because if you open the folder, there will be the exe file, and then there will be maybe, I don't know, 100 files with DLLs and a lot of files, and you don't know where to start. So if you open one DLL, you look inside, you say, okay, that's a lot of code, a lot of functions, and I don't know at all where I would start. So what I always do, and what's easy to do, is this. Who is using Linux in this room, or Mac? Okay, a lot of people. So cat, you know cat, you know strings, right? That's a tool. You pipe in binary string, and it will only output what is printable. And then you grab inside this string, and you grab Y. You get X, you grab Y. What is X? X is some file you want to explore. So I don't know, application.exe, and Y is the ASCII string to search. So you search for some good things like key, decrypt, AS, or you simply look at the whole of the ASCII which is printed out. And what once happened to me, I found that in the exe file, exe is basically an archive. So inside you can really wrap in anything. And the guy who was developing the tool, he had an Excel file where he was writing what needs to be done during the development. And when he built the software, he compiled in the XLS file, the Excel file basically. So once I was analyzing it like this, and I said, this looks like some bullets. It's weird. It's like inside. It is nowhere on the GUI. You don't see those strings. So I analyzed more, and then I found out that there was even email of the developer, and and there was his name, and what I really liked is that there was something like implement the method to change default key, and then there were 5 first bytes of the key, like the default key, so that he knows which one it is, and first 5 bytes in hexadecimal of the key, and then 3 dots. And I said oh, he could have written it entirely, because I would have it, but I only have the first 5 bytes. But I already knew where to look. And a very funny thing, and then I come to the very first part of the steps you should take when you analyze a device as a black hat or white hat, is you should look at the documentation, because I had the beginning of the key, and we had a coffee together together with our sales guy, and he's very active, and he always thinks like, let's just do it simple. I will use ChatGPT or something. I will get it done fast. Then I explain to him, no, slow down. It's not so easy. It cannot be done so simply. It's more complex like that. It's not so simple. And then he came and said, you told me it is starting the key with E6 and some bytes, and he just showed me some user manual for it was not official manual from the manufacturer, but it was manual from some company who was reselling the product, and there was a print screen with a very small, in the documentation there was a print screen of the configuration software, and in the configuration software there was a picture which you could not see on a first view, but he zoomed in the picture and it was barely visible, but it was visible, and there was the whole key written on the picture. And he told me why are you trying to use all those tools? I just look in the documentation and I have the key. So that was funny, and I think they are not aware of it that it is there. They just print screen it and it is there. So really, documentation is important to explore. Okay, but I will get back to this. So you use this to analyze. It will basically print you all printable characters which are there in a binary. And if you find a binary which contains interesting strings, you will analyze this binary first, because otherwise you could get lost in the amount of binary things which are there. So you would not find the right thing in a limited amount of time. So when you find a file which looks interesting, you can continue, and you can open it with one of the tools, either Hydra or Binary Ninja. But before I will show you that, I will very quickly tell you something about Hydra. So it was developed as open source by NSA, as the American agency. The last release is from April 11, so it is supported. Plugins can be written in Python, so if you can think of some specific analysis you would like to do, you can write a plugin in Python which will help you do something which you don't want to do manually. It supports x86, ARM, MSP 400, PIC16, really a lot of architectures. Originally it was closed, but NSA decided to release it as open source in March 2019, which is interesting. They just give it to world, and anybody can run analysis now. I think the reason why they did it is because it's also a good pressure for companies to implement security. Of course, you risk to pay 10 million euro, but you also risk to be hacked publicly. That's not good. Okay, so this is how it looks like. The first row can maybe see something. Last row, I think, can't, but I will describe. So the central part shows the binary itself, and it shows the opcode and assembly instructions. And the right side here shows the pseudo C code. So it's optimized C code. It's hard to read, but you can read through it. And if you have debug symbols, you can even see the name of the function. And if there was a good programmer who named the functions well, you know where to look, and you only explore the functions which are important to you. So another good hint I can give you, if you compile your tool, not even the firmware, but also tools, but firmware as well, always strip debug symbols, because then the analysis will be much, much harder. But here there are no debug symbols, so the function is named like fun underscore 0040 and the address of it, so it is hard to guess what it does. But when you have this pseudocode, what you can do, for example, when you know that there is some integrity checking inside of the function which generates the frame, you can look for something like XOR 0x1021, which you maybe know what it is. It is a polynomial for CRC16 CCIT, which is like CRC16 algorithm, and it is used very often. So if you know there is CRC16 used, there is maybe 20 of them, You can just look in the C. If it is used somewhere, you XOR with this constant. If you find it, you know, okay, this function does CRC calculation, and then you can see, and where it is called. It is called here. What is done before it's done deciphering. Yeah, and like this you can find the right spot in the binary even if you don't have the debug symbols. Next tool is called Binary Ninja. It's not so it's like it doesn't exist so long. It is more closed. Free plan is available for x86 application, and I used it, and I think it is a little bit more user-friendly for beginners. And here is an example. So there is a manufacturer. I have whitened the right spot so that it's not visible, because you could maybe deduce what's the name of the manufacturer, but like this it's completely anonymous. Which is not using AES for encryption, but instead they are using the ID, and then they are doing some XORing with the ID. Of course, the algorithm is not publicly open, and we wanted to have it. So we have found the DLL, and you can see here on the left side the names of the function. They don't call the function fun as in Ghidra, but they call it sub, like subroutine, and then the hexadecimal address of it. But if there are debug symbols, or if some symbols in the DLL are exported, you have the name. And when I did this get x strings grep and decrypt or crypt, I found this something underscore decrypt function, which I said, yeah, that's it. That's the decrypt function. It cannot be so easy. I couldn't believe it. It was 2 o'clock in the morning. So I said, okay, let's look at it. I opened the binary, and already I could hear the bird singing outside. It was 4 o'clock in the morning, and I checked the inside of this function, and I could see that there are 2 subroutines which are called, and in this subroutine I could already see that there is something like 14 bytes, which is the total length of the frame, which contains all the data. I know at the end there is the CRC, and I slowly have rewritten this pseudo C code in Python. Then I took the raw frame, which I was able to capture it, but I was not able to decipher it. I just ran it, and then 5 o'clock in the morning I saw the water consumption, and it's a really the feelings you feel at the moment is not possible to describe. So this is like the keyless ciphering. I call it the keyless ciphering, which is used there. There is a key, but the key can be computed from if you have enough number of frames. And if I would release how this can be done, then the whole key distribution for this is completely useless. And what's even worse, in their documentation, and I don't tell who it is, they proclaim, they call the key as AES key. They don't say they are using like AES encryption or what AES encryption they are using, but they call the key AES key, and the key is 16 byte. So if you, as a user, buy the product, you believe it, like, yeah, of course 16 byte AES will be like AES encryption. You buy 1 million of the water meter, that's not a problem. We have information in Dubai, there is 5 million of this water meter deployed, for example. And then you realize that it's basically open. And well, even like the distributor will deploy it with the default key, so that's already bad. Yeah. But even if they don't deploy it with the default key, I found a way how you could, if you capture, I think, 256 frames, and the device is transmitting every 15 seconds. You can compute the key, which is a complete security disaster for this product. But I will never release it, and I have hidden it because this would be really a disaster for the company from security point of view. Of course, if you check the webpage of the company, they proclaim that security is the most important thing, but that's the marketing, yeah, that's not the development. It's very, very sad. Okay, and now the dynamic runtime analysis. What's the idea? Sometimes direct static analysis of the binary is non-trivial. If you have just a binary and you analyze it, it's hard to find the right spot. But if the device you analyze and the manufacturer was so kind that he didn't close the debug port, what you can do, you can use like all known Eclipse-based tools to connect to the device. Sometimes it is not good to reset the device, but it is also possible to connect to the debug port without resetting the device. So if there is something in the RAM which prevents, when the device is reset, some error is set and then the device doesn't function as normally, it is good to have at least maybe 20 of the devices so that you can try multiple times and you basically consume one device for each trial. But you could see that the price of the device is $20, so it's not that the price you pay is not that high. But what you can do, you can analyze the binary as it is running, and you can see the assembly and you can step through it. And you can think of it, okay, but how do I know where should I look? And from that, I have a good advice. You can do this down to up approach. I call it down to up because when you see the PCB, you have a microcontroller, you have the radio chip, and there is some SPI between them. Well, how can they send data to the radio chip? Using the SPI. What is the address of the SPI register for the transmission? You find it in the data sheet, some address. Then you scan through the disassembly of the binary, and you find an instruction which is writing to this specific address, and you have the point at which the firmware is pumping the data into the radio. And then you are simply stepping back. You identify where the payload is created, where the payload is encrypted, and then you analyze the assembly and you have the encryption algorithm. That's it. It's easy. Yeah? So even if you don't have any debug symbols, you have no information, but you have the hardware. And you can use the information about the hardware so that you know where to start. And it is not possible to prevent this. If you use some SPI to transmit the data, you must write to that register. So the attacker will find the right place and then will be able to do this backstepping until he finds the right place where you create the payload. And I will show you this here. Yeah, so this is how it looks like. You connect, this is what Eclipse-based, I don't show what, but I already said it that it's MSP 430, but you would see it here are the instructions. So if you look at the instruction set, I bet that you guessed that it's MSP 430. And what you can see on the upper left side is this like memory view, so the content of the memory, and we know what value was sent over. So we found the value in the binary stream because very often it is saved as a little endian 16-bit or little endian 2-bit variable. So you simply find it. Then we found where this area is being modified. You can use things like memory breakpoints. So you can tell stop the program when somebody writes to that address. You can use all the bug features which are available from the chip to analyze the binary. You can use what I mentioned, that you can see when he's writing to special function registers. You can see the special function registers here, so you can see in what state the device is. You can of course disable by writing to special function register the watchdog, so that the watchdog doesn't kill you when you do the stepping and when you pause the execution, etc. You can see the registers of the core. When the program is advancing, it is modifying the registers and then storing the data into the memory. You can have a lot of breakpoints, and you simply step through it, and you write. You learn a new assembly. If you didn't know how to program in MSP 430 assembly, you will learn it on the way, and you go and you rewrite the algorithm on a piece of paper. I can tell you that in this case there were like two constant binary arrays against which the data were XORed, and then there was another XORing which was done differently, and there was some table which was taking the byte and then it was rearranging it in a way. So there was shuffling, there was XORing, but again there was not a unique key per device key because the manufacturer said maybe in the design of the device, no, it's too complex to provision every device. We will have a binary, nobody will guess this, it's crazy. Tube sorting, there's byte shuffling, it's impossible to guess. Well, it's impossible to guess, but when you have the binary, you have it. Yeah, so that's it. Okay, and now I will show the practical part, which is only 10 minutes. So what you will see power analysis, you will see UR display analysis, and you will see the spectrum as well. Just a very quick description of the system. So our device is here, the 2 antennas and the 3 blocks. It is receiving a wireless M-bus heat cost allocator, which is using IS-128 encryption, and is using wireless M-bus T1 mode, using this radio, this microcontroller, and then over UART we talk to narrowband IoT modem, and we send through narrowband IoT using UDP and IPsec encryption, because we are in a private APN, and we talk to some virtual private server. Why I show you this this slide is just to explain why I'm hacking my own device and why I don't think it is bad, because the data are source encrypted. So even if in this setup like this device is not secure, or is not trying to be secure, because it doesn't need to be secure, because the data is end-to-end encrypted. This is very important. Yeah, so just to understand, I will now run the video. I have and the audio is not working, so I will describe it myself. So you can see the cellular logic on the upper left side. Down on the bottom side, you can see OT Koitek. Here you can see spectrum, and there is a web camera of the setup. If I would need to transport this in train to Prague, I'm quite sure that all the wires would break, so that's why I put it like this on a video. So what you can see, the signals which are connected to cellular logic. First, 3 signals are UART lines, which are identified on the board. Let's just imagine I'm an attacker, so I identified, okay, this is UART going from the microcontroller, so let's connect there. And the last 4 lines are SPI between the microcontroller and the radio, which is SX1261 from something. So now I start the measurement, but I didn't turn on the power, so the consumption is close to 0. I will turn on the power. You can see already some profile at the beginning, which is the boot of the device, and you can see that already on the UART something is happening. And what's quite interesting is that you can interleave the output of the UART, and you can put it in a form of a console. So you can see what is printed by the device, what data are exchanged between the narrowband IoT module and the microcontroller back and forth. So that's why I say this device is not only for hacking, but it is very good for development as well, when you want to debug something. And on the lower part, you see the power profile. So at a certain moment, the device is now connecting, so you can see peaks during the connection. And when it connects, it will, now it is, this was the bootloader, and now it received 4B, so it booted. Yeah, so this was the boot, I think, and entering sleep mode. And after a moment, we should see here that the power consumption goes low, and we will see here like the current value. After selecting that, we will have something like 14 microampere, like this, 12 microampere. So you can see the device is sleeping and only the module is talking to the network, waiting for some inbound communication. You can deduce that from the power profile. And and of course you can see it from the console because the device says entering sleep mode. We woke it up. You could see that a new thing happened. There is communication with the SPI line. So the radio is set up and the data is received. And what I will show later is when the data is received, I will stop the record for the SADA logic, and I will show how from the captured SPI communication I can calculate what is. Yeah, you could see it received something, and now it is sending it to narrowband IoT. So you could see there was on the SPI line a communication, and then there was a communication on the UART. And from the printout of the console, because well, it is not trying to hide anything; it's showing transparently what's happening. So this is really like a low-tech example of analysis. It received something there, and then it started communicating. So I know that at this part, I will see the setup of the radio, reception, and I will see the readout of the data from the meter, which is then here sent out. Yeah, and by the way, the SDR, there is not much I could really show. I'm just showing that here this frequency is 868,950, and that there are peaks, which are the smart meters, which are transmitting in the vicinity. And some of them is this input allocated. So what I do now, I'm looking for the carrier frequency. So I open the datasheet of the SX461, and I check that to set the carrier frequency, you need to write to opcode 0x86. So what I will do, I will switch to a different view in the SADA logic. And in this view, I don't put there the output of the serial lines, but I put there output of the SPI, and I will look for the 0x86, and I need the right direction. This is the direction from the microcontroller to the radio. And when there is 0x86, I can suppose that it is the command to set the carrier frequency. So I click there. You can see this is user friendly. It goes to the right place where I need. I don't need to manually scan through the hexadecimal record, so I found it. And I found this bytes which follow, which is 36 for F35-8E. And if I simply check the documentation, and I open a Python as a calculator in interactive mode, and I will just write this hexadecimal value, so it's 0x. Come on, alright, write it. Yeah, so these are the bytes which follow. You can see it in the documentation. 36, 4F, 35, and 8E. You can see it translates to 911 million and something, which is not 911 megahertz is not the frequency. But if we look again in the documentation, we should multiply by the crystal frequency and divide it by 2 to the power of 25. So we will just do that. And if I check the board, I can see that there is 32 megahertz crystal. So either I see it or I can guess it, because I know it should fall somewhere in the 868 band. And then I divide it by 2 to the power of 25, and I have the frequency, which is 868,950. Yeah, so if you, as a manufacturer, have some custom frequency which you use, so you say, okay, the guy will not guess it, because it's custom frequency, it's obfuscated, it's double XORed, it's completely secure. You will present that to your CEO, and the CEO will say, yeah, well, to me it looks fine. And of course, to 99% of people it will look fine, but there is the 1% which is always there and can do the analysis. So, and then of course, if you don't use key distribution and you use the same key everywhere, you have a problem. Yeah. Okay. So I think this was the main thing I wanted to show from the practical example. I will quickly check whether there is something more, but the time is starting to be up. So yeah, there should be already coffee break. So feel free to either watch or you can ask questions if you want during the time. But yeah, I'm here showing the frequency band just to explain the SDR. And the power analysis, we could look at it closer, but you can see transmissions, receptions, processing, and then speed. So yeah. So this would be for the quick overview of how the tools can be used. And now I would maybe, I think that's the main thing. I'm just showing that you can correlate also the information I wanted to say at the end of the video is that, and you can find the video on YouTube, so you can watch it with the original comment, which is much better than this one. You can always correlate power consumption, communication, and spectrum. So you can really see what's happening. And even if you don't know what's happening, by seeing a lot of inputs, you can realize something. It's not, the interesting part of analysis is that you are trying to find something and you don't know what you are looking for. You know approximately what you are looking for, but you don't know exactly. So it is good to see the things in the context of each other. That's the idea I wanted to say at the end. Okay, so I will very quickly switch back to the presentation. There is the last slide there. And the slide is, yeah, this is another example of device where there is a wired N bus connected to our device, and then we wirelessly, using wireless N bus, transmit the data from the wired N bus. And here, this part is wired with no encryption by design, so it should be maybe protected at physical level. But then here is our device, which captures the wired N bus and transmits that to wirelessly. So you can think of, okay, here we introduce the security issue, but we don't, because we do in our device key provisioning for each device. Each device has a unique key burned into OTP. We use IS-128 CPR mode, so it stays secure. Just to give you an example, there is a video on our YouTube channel which you can watch, and I explain it there. And yeah, and the key, and now the very last slide is the takeaways. So it was mentioned in the presentation from Nicola, always keep security in mind, and even during design. Yeah, it's not after the design, but it's during the design. You should take care of it. Think about what is your asset to protect. If you share the same key everywhere, your assets to protect is the whole product line, which is a lot. Yeah, keep the asset you need to protect as small as possible. If somebody hacks a single device, it's not a problem. If somebody hacks the whole product line, it's a problem. Use standard ciphering algorithms and standards in general. Yeah, open metering standard, etc. If you are in the smart metering industry, store keys securely, randomize the key, and do a proper provisioning. And this is interesting part, try to allocate a developer to find weak points, some kind of byte hacker. Yeah, so of course you have a developer, you have tester, you have somebody who do code review, but now there is this new initiative that you should comply with some cybersecurity. It is a good idea to have a white hacker in your team, or you can call us. And understand any and all technology you use in your product. If you use some stack, wireless N bus stack, Waravan stack, you just use it. You look for echo example or some ping pong example or hello world example with this wireless stack. You just modify it and wow, I have a product. No, you don't. You need to understand the stack, what's happening inside, so that you can really take care of the security. If you use some open source, you need to know how it works and what are the security problems which can arise. And to go further, I wanted to mention, so that it's at least mentioned in the presentation, always start your design by designing how you will update the firmware in your device and how you will update it securely. And of course, last thing but not least is think about key revocation. So if you deploy the key and you know it was breached, think of a way how you can reinstall the key so that it can continue to function securely. Because maybe your device will not be hacked, but maybe the database with the keys can be leaked. So it is good to have a way how to revocate the key, or to have more keys in the device, more unique keys, and you simply say, don't use number 1, start using number 2, and you know what is the number 2, and you will have a different place where you store number 2 keys. So if one database is leaked, this other is not. Security is not complex. It's about analyzing what you do, analyzing how you design it, and also trying to destroy what you built. Yeah, that's how you should think of it. So that's it. Thank you for your attention, and if you have any question, feel free to ask now or during the coffee break, which should follow, but will be short because I have eaten some of the time. Sorry for that. Thank you.